I am Cristina Vallés. I'm a lecturer in Polymer Nanocomposites at the Department of Materials, University of Manchester, and I'm based at the Henry Royce Institute and National Graphene Institute. And I'm going to talk about epoxy nanocomposites as structural adhesives for Joule composites repair and bond and selective debonding. So my group's research encompasses multiple multidisciplinary research projects in a wide range of areas, including production and modification of nanomaterials, carbon nanotubes, graphene, as well as other 2D nanomaterials. And we also explore different applications in which these nanomaterials can make a strong impact, such as multifunctional coatings, energy storage, flexible and wearable electronics, and structural composites and structural nanocomposites. And in particular today, I'm going to show you some recent research we've done on structural and multifunctional nanocomposites. So as we probably all know, carbon fiber reinforced polymers are widely used in many industrial sectors, in particular in the aerospace and automotive sectors, because they offer a high number of advantages, including high specific strength and stiffness, low density, easy integration into consolidated components, and a good design versatility. Now, due to these new targets for lower CO2 emissions and the subsequent need for lightweight structures, the global demand for these materials, for these composites, is expected to increase very rapidly in the next years, as we can see here. This, of course, and unfortunately, will cause major environmental challenges in waste management, and that's why novel, efficient, and sustainable techniques for composites repair are currently on great demand. So, heat-activated polymeric adhesives, and in particular epoxy resins, are widely used in industry as structural adhesives to join composites, as we can see here. So they put two pieces of composite together, they bond them together in order to fabricate and manufacture these larger and more complex components which are going to be used in industry. As we probably all know, epoxy resins are fluid materials initially, and that's why they can be very easily spread here in the bonding area between these two pieces of composites. However, then we need to cure it, we need to promote these chemical reactions, we need to promote a cross-linking between the polymer chains in order to go from this initial fluid state towards a solid state where the epoxy will show its maximum potential and in particular its optimal mechanical properties. This curing, this cross-linking is typically done in an oven or autoclave. However, as we can imagine, there are a number of disadvantages typically associated with the use of an oven or autoclave, being size limitation, energy consumption, and lack of localized heating, some of the most relevant ones. In industry, they are already starting to use out-of-autoclave repair methods in order to avoid using an oven or autoclave for this purpose. For example, they use heat blankets, heat lamps, or IR heaters. And these techniques work quite well in general, and in particular when they want to bond or repair flat or very simple geometries. However, some issues start to appear when they want to bond more complex geometries. In addition, in these cases, the heat is applied externally, the heat is applied from outside, which leads, unfortunately, to a lack of thermal uniformity all over the bonding area, as well as to sometimes a considerable heat loss. And finally, these methods clearly lack a vision of circular products and sustainability. They are focused on bonding, manufacturing. However, they do not pay much attention at the moment on the fact that at some point, for example, at the end of these components' life, it will be interesting, it will be important to be able to deconstruct them or debond them, going towards circularity in the field of composites. So an adhesive capable of generating heat internally from inside emerges as a very good alternative to all these techniques I have just mentioned. because this will allow an effective, controlled, and localized heating of the repaired area. So basically, we will be applying heat only in the interesting part, in the bonding area, without heating anything else. And it will also allow a selective debonding. More specifically, electrically conductive epoxy nanocomposites emerge as very good candidates because they offer very good Joule heating properties, as we are going to see afterwards. But basically, once we are above the percolation threshold, when we have an electrically conductive nanocomposite, it has the ability to transform an electric current into heat, generating heat from inside, internally, as we are going to see afterwards in more detail. And in addition, only a nanostructured electrical component will actually fit within the bonding lines, which required thickness is normally in the range of a few hundreds of microns. So in this particular project, we wanted to find an answer to 3 key questions. The first one was, can electrically conductive nanocomposites cure thermosets out of the oven through a Joule heating effect? If the answer is yes, can we use these electrically conductive nanocomposites as structural adhesives for out-of-autoclave composites repair? And again, if the answer is yes, can we use a similar approach in order to go the other way around, in order to deconstruct these bonded joints in a selective way, going towards circular products and sustainability in the field of composites? So, as we probably all know, when we incorporate an electrically conductive nanofiller, for example, graphene, into a non-conductive polymer, for example, epoxy, we will see this behavior, the typical behavior of an percolated system. Basically, when we are at very low loadings of filler, even though they are electrically conductive, since they are not in contact with each other, this material won't be conductive. We won't be able to measure any conductivity. We need to add more and more conductive filler in order to start creating these conductive paths. And once we are above the percolation threshold, if we keep adding more and more conductive filler, we will be creating more and more conductive paths, and we will be developing this 3D electrically conductive network embedded into the polymer matrix. So this material is electrically conductive, and at the beginning of this project, we wanted to explore the potential of these electrically conductive nanocomposites for resistive thermoset curing through a Joule heating effect of this electrically conductive network of graphene incorporated into the polymer matrix in order to develop a novel out-of-autoclave curing method. So the first thing we did, of course, was to fabricate graphene epoxy nanocomposites at different loadings of graphene, of course, cured in the oven, in order to determine the percolation threshold. So we tested the electrical conductivity of all of them, and as expected, and as we can see here, this system behaved as a percolated system, and we could use the classic percolation theory to determine the percolation threshold, which was, in this particular case, around 8 to 8%. So once we are above the percolation threshold, we found that when we apply an electric current through this uncured system, this electrically conductive network of graphene incorporated into the polymer could effectively transform the electric current into heat, generating heat from inside through a very simple Joule heating effect, and successfully curing completely the nanocomposite. We could control this generated Joule heat very easily using an IR camera, as we can see here. And we found that by controlling the voltage, the applied voltage, we could actually control the heating rate, the achieved temperature, and we could also maintain the desired temperature for a particular number of hours, depending on the required conditions to completely cure a particular epoxy system. This generated Joule heat was enough to completely cure the nanocomposite, and as we can see from this DSC data, the level of curing achieved using this Joule heating induced curing method was quite similar to the level of curing achieved using the oven curing method. Of course, we wanted to test the mechanical properties of these two nanocomposites cured in the oven and cured electrically. And we found that the modulus, tensile strength, and strain at break were very similar in both cases. So this shows that this Joule heating-induced curing method shows great potential as an out-of-autoclave thermoset curing method. We are actually achieving very high levels of curing, and we are not compromising the mechanical properties relative to those we would find if we were using the conventional oven curing method. So from this point, and to go one step forward, we started to wonder, would it be possible to use these electrically conductive nanocomposite mixtures as conductive adhesives to repair composites through Joule heat curing. Basically, we have here two pieces of composite. We will put a little bit of our adhesive here in between them both all throughout the bonding area. We will apply an electric current, and once the adhesive is completely cured, then we can say that the composite has been repaired or bonded together. In this case, due to the thickness required for the bonding line, the model system had to be this nanocomposite film rather than the bulk nanocomposite we have just seen, which basically meant that we needed to revisit the percolation theory to redetermine the percolation threshold in this direction out of plane, because this is the direction along which we are going to apply the electric currents during the process of curing or repairing. We found that in this direction, the percolation threshold was 3%, around 3%, which basically means that any loading above 3% should work for this particular application. So we tried 3%, 5%, and 8% graphene, and we found that the three of them worked quite well. So the electrically conductive 3D network of graphene incorporated into the matrix could successfully transform the electric current into heat in the three cases, successfully curing the adhesive, and then successfully repairing the composite. From this IR camera, we can see that the generated Joule heat was quite homogeneously distributed all over the bonding area in all the cases, independently of the formulation of the adhesive, so independently of the amount of graphene incorporated into it. However, we found that there was a strong dependency between the heating rate and the formulation of the adhesive. As we can see from this graph, the higher the amount of graphene, the faster we can actually achieve 100 degrees, which in this case was the desired temperature. And this is related to the electrical conductivity. When we have more and more, we are adding more and more graphene, of course, the electrical conductivity of the nanocomposite is higher, and that's why we can achieve the desired temperature faster using the same voltage. And this was actually very good news for us in the sense that this will allow us to control the curing conditions or repairing conditions just by controlling the formulation of our adhesive. We tested the mechanical properties of the bonded joints of the samples cured in the oven and cured electrically by single lab shear tests. And here we see the obtained results. We see that the lab shear strength was very similar in all the cases, independently of the formulation of the adhesive and also independently of the curing method employed. This suggests that these mixtures, these electrically conductive mixtures, seem to be quite effective as conductive adhesives to repair composites through Joule heat curing without compromising the mechanical properties. Of course, we wanted to investigate the failure mechanism of the bonded joints. For us, it is very important to understand and to know what's happening during failure so that we can actually decide which direction to take in order to keep improving the mechanical properties of these repaired samples. There are three different types of failure behavior depending on where the failure happens during the test. The first one is the adhesive or interfacial failure mechanism, where the failure happens here at the interface between adhesive and adherent, and it is typically associated with a relatively weak interface between these two components. The second one is the cohesive failure mechanism, where the failure happens here within the adhesive, And this, of course, is related to strong interfaces between both of them, or stronger relative to the first situation. And then we have this third situation where both failure mechanisms coexist in the same sample. So we'll see in some regions, we'll see that it is the cohesive failure mechanism, the one dominating the system, and in other regions, it will be the other one, the mechanism dominating the system. So what's happening in our samples? Here we see an SEM picture corresponding to the fracture surface after lab shear test when pure epoxy or neat epoxy is used as adhesive and of course cured in the oven because it is not electrically conductive. We see the presence of quite clean fibers coming from the composite, which suggests that it is, in this case, it is the interfacial failure mechanism, the one dominating the system, and as I have just mentioned, this is related to a weak adhesion between both components. Now, what happens when we add graphene to our adhesive? In this case, we see the presence of fibers, again, from the composite. However, we start seeing the presence of some debris coming from residue coming from the adhesive, coming from the nanocomposite. This suggests that both cohesive and interfacial failure mechanisms are coexisting in the same sample, and we also see a progressively increasing dominance of the cohesive over the interfacial failure mechanism as the filler loading increases. Indeed, we see that as we go from 3% to 5% to 8%, we see more and more regions covered by this residue from the adhesive, which suggests that we are actually creating increasingly stronger and stronger interfaces as we are adding more and more graphene to our adhesive. In any case, the mechanism of failure did not seem to depend on the curing method. We see very similar results for the oven-cured samples and for the Joule-cured samples. And now probably novel strategies to improve the toughness of the nanocomposite, the adhesive, need to be developed in order to keep improving the mechanical properties of the bonded joints of our repaired samples. So finally, the third question we wanted to find an answer to is a selective debonding possible? In order to realize this idea, it is important that we pay attention to that we select strategically the epoxy used to manufacture the composite and the epoxy used to formulate our adhesive. The TG of the composite needs to be considerably higher than the TG of the adhesive so that we can actually Joule heat the bonded joints up to a temperature which is in between them both to make sure we are actually softening the adhesive for an easy deconstruction without altering or damaging the components or the composite. Here we see that when we are graphing into our adhesive, into the epoxy, we are progressively increasing the TG. However, in all the cases, we are well below the TG of the composites as required for an effective selective bond deconstruction. And here we see that when we Joule heat the bonded joints at increasing temperatures, we are progressively decreasing the lab shear strengths. We are making the deconstruction increasingly easier. And in particular, when we are above the TG of the adhesive, we can see that the lab shear strength is particularly low. It's very, very low, which means that the deconstruction is very easy and we don't need to apply a lot of energy and we are not damaging the composite, the structural properties of the composite. Finally, what about the Joule debonding mechanism? Here we see some SEM pictures corresponding to the fracture surface after Joule debonding using different experimental conditions. And we see that when as we increase the Joule debonding temperature and the amount of graphene incorporated into our adhesive, we are promoting progressively the cohesive failure mechanism, whereas lower Joule debonding temperatures and lower amounts of graphene incorporated into the adhesive tend to progressively promote the adhesive failure mechanism, which basically means that we can indeed control the joints failure just by controlling the adhesives formulation and the Joule heating conditions. And this, of course, is very good news for us because this will allow us to find the right balance between recovering the undamaged adherents and minimizing the work required to recondition the surface for future use. So summarizing, we've seen that these graphene epoxy nanocomposites can be successfully cured by Joule heating of the conductive network of flakes formed in the matrix when we are above percolation. We've seen that these nanocomposites seem to have great potential as structural adhesives for Joule composites repair or bonds, and we've also seen that a selective Joule debonding is possible, going towards circularity in the field and improved waste management. Before finishing, I would like to thank people working with me in this project, the funders, and of course, thank you for your attention.
Thank you, Cristina. Again, for me, very interesting. Thinking of any of that learning can be applied to recycling carbon fibre as well, so there's conversation. Any questions? Dave. Let me start. Dave. There's a microphone coming in.
Thank you, very interesting presentation. I think I've got 3 questions, which won't surprise James. We're already using Joule heating in moulds to cure composites. Given the increasing use of graphene, this is the first question, given the increasing use of graphene in the composite materials themselves, in structures, etc., do you see the potential to actually cure the composite itself using the embedded graphene? Second question is, could we use induction? And related to that, the third question is terrorism. If you do all of that and you can use it where you want to use it, could someone direct something that could then disassemble your part?
So yeah, thank you very much. Very interesting questions. The first one, I guess in terms of manufacturing composites, we can use this technique. The only problem I see here is more or less the scaling up, because if you need to fill the epoxy resin, all the epoxy resin you are actually using for the whole components, for example, with graphene, that means that you are going to need a lot of graphene. However, technically, I think it should be possible. I guess that's probably the limitation.
It's cheaper than buying an autoclave.
Sorry?
It's cheaper than buying an autoclave.
Well, yeah, of course. But I think in theory, technically, I would say it should work, because once you have an electrically conductive, you are above the electrical percolation, it should work, and you can actually optimize all the conditions like voltage and all the other conditions in order to find the right curing, the correct curing, to optimize the process for each particular case. The second one was induction. I think it works, and I think there are also some articles already out there. Of course, we think that this method has some advantages with respect to methods that already exist, because in this case you can use this method for carbon fiber reinforced polymers, but also for other types of materials. For example, you can use it for carbon fiber composites, or glass fiber composites, and I think you can actually use it for a wide range of different types of materials. And then the third one, I have to say that I had never thought about that in particular. But I think from the preliminary results we have so far, in each particular case, you need to optimize the conditions you need for the optimal debonding. So I guess in each particular case, you should do a little bit of investigation to optimize the process. So, if you know the formulation of your adhesive, probably only you will know how to debond them, I guess. But yeah, that's a very interesting point, I guess.
Thank you.
Follow that through tomorrow. We have the BAC, people there tomorrow, there is a BAC mono with the graphene, I think some of the tooling. but I think the repair has always been one of the challenges for aerospace, automotive.
Yeah.
So I think this is an area for me. I remember seeing this 8-9 years ago as an idea and a concept, so it's great to see that develop. But how it might be commercialised is a very interesting area. Third question, Faye, I think you've got a funny mind there, so I'll have to think about that one. But it's a very good question.
One question. Thank you so much for your presentation. It was interesting. I'm wondering, what do you think about the adaptation of this technology in thermoplastic composites, aerospace composite like PEEK, and also hybrid composite, thermoset and thermoplastics?
At the moment, I have a PhD student who is working on thermoplastic welding. We are using a similar strategy. However, in that case, we are preparing graphene thermoplastic nanocomposites as a heating component for thermoplastic welding. In that case, it's 100% thermoplastic. At the moment, we are working on a model system which is PC. And the next step will be to go towards a little bit more challenging polymers, such as PEEK, of course. Yeah. So we will use similar technology. Of course, it will be a little bit more challenging because you will need higher temperatures. But that's the next step of this particular PhD. And then I guess your second question was about like hybrid.
Yeah, hybrid thermoset and thermoplastic together. Maybe you can adapt this technology.
We could, yeah. I think that we haven't done that yet, but of course that would be really interesting, and I guess it should work. Maybe it will require some optimization, but it should work. And also, it should also work if you use, for example, polymer and metal, for example, which is something
also
we are
metal, metal thermoset, metal thermoplastic together.
Yeah,
with the same formulation, maybe it can be adaptable.
Yes, yeah.
Yeah. Okay, thank you.
Thanks.
Another interesting conversation to talk about maybe tomorrow is how we might take some of that forward as a trial almost. I can see the commercial benefits of doing some of that would be very interesting. Any other questions, Cristina? Okay, thank you very much again.
Thank you.
Fantastic presentation.